actually this part is one of the most tedious parts of this lecture. So I expect many of you have some trouble to understand these issues. Mass spectrometry actually one semester course. Well, one semester course, especially who majors in analytical chemistry, in chemistry department. For your environmental science department, this course is not open. But my supervisor, he's a major of analytical chemistry, so I run this course. So I'm teaching mass spectrometry. So I try to pick up very important topic and very easy topic for this part, but I'm not sure how much you can understand. Okay? But I try to explain very easily. Okay, the principle of mass spectrometry is make neutral molecule into ion. It's actually positive ion or negative ions, but generally our target are positive ions. So MOZ value, mass to charge ratio, I already explained. Molecular weight and charge plus 1 or plus 2 or plus 3. It depends on the method of ionization. But the mass spectrometer, some people think mass spectrometer can measure molecular weight. No. It can calculate, detect MOZ values, not mass. So this is just scheme, the overall scheme of mass spectrometers. The first one is sample inlet and ion source. We make neutral molecule into ions, so it is called ion source. And further is mass analyzer. We want to separate different ions according to their MOZ value. And detector. MS is self-detector, but there is a more specific detector. Okay. Lastly, data system. So sample inlet generally here is the atmospheric pressure or some concentration. And for this reason, ion source and mass analyzer and detector, we require high vacuum. So we need to turbo pump to remove other gaseous molecules. In ambient air, about 8% of air is N2 and 20% of oxygen. So these gases should be removed. So our purpose is only introduce our organic molecule into this system. For example, for sample inlet, GC and SC we have already studied. And another thing is DIP and DP. And for ion source type, EI, CI, FAT, MARDI, and ESI are used. So there are many options actually. And for mass analyzer, magnetic sector, electric sector, double focusing. This is a combination of magnetic and electric. And color pole, this is one of the widely used benchtop small scale GCMS. And ion trap, IT, ion trap, and Fourier transform ICR, and TOF, time of flight. So there are many combinations of mass analyzer. So when you see the product of MS, you can make, say, GCMS, GC top, GCITMS, and so on. It's combination. So any kind of combination is used, but generally we use GC EI quadruple or GC EI double focusing HRMS or HRMS. And for LC and ESI, and then quadruple or ion trap or top are general options. Okay. So So Fab and RD is widely used for the biomolecule and large molecule. So our concern is a relatively small molecular weight about around 300 or 400 up to 400. So for the cases we use EI and CI or ESI. So today I'd like to explain EI, CI, ESI, and this one, biology sector and protocol, and trend and top. Okay, this is simple instructions, DIP and DP. This is not widely used for power sources. For solid or mass or liquid, is we can use this one. But our general option is GC or SC. And EI, electron ionization. This is the EI source. Okay, the real photon. So EI means we can make neutral molecule into ion during the positive ions using EI, electron ionization. Here is a filament of the metal, and there is some electric energy input, and then there is an ejection of the electron. So we say electron beam, like a gun. There is a continuous ejection of the electron. And when our sample molecule enters into this area, our molecule, and there is an electron beam on bottom. Okay? And then some molecule have a electron infection, and then the molecule lose one electron or two electrons. Molecules infected by electron, they lose one electron. This is an N plus. If they lose two electrons, this is N2 plus. Okay. It becomes ions. So there are many types of EI processes. So the molecular, this is our molecule ABC with the different atoms and electron infection, and then it becomes ABC plus or ABC plus 2 plus, or the separation of fragmentation of our molecule into AB, C, A plus BC, and so on. There are so many combinations for the electron infections. It means that if there's an apple and we shoot the apple becomes fragmented. Sometimes apple just show exists the same shape. But sometimes some apple can be broken down into the two parts, or sometimes become very small pieces. So like these procedures. So this is more as a combination. So A, B, Y, Z, G become this kind of fragmentation ions. So this is an example for EI mass spectrum. At 17 electron volt potential, this is 17 electron volt potential. This is the power of electron infection. So this is a general option, 17 electron volts. All the GCMS quantum use, they use 14 values this one. So any chemical, they are infected by this electron volt, show their stable, very constant fragmentation patterns, whatever the instruments. Okay, so this is general option. So this case is molecular weight is a big one, MO cigarette is this one, and then it makes very small peak. Other fragmentation show much stronger problems. And for rather soft ionization, small power, it contains large peak of MO0, molecular weight peak. Okay. For these cases, there is a MO0 value, so we can use this one. But sometimes we lose this peak, and then it's better to use EI or ESI or CI later in the explain. So many chemicals have their own fragmentation patterns. Is in the mass level. So probably for many chemicals, most of our Thai chemicals have their own fragmentation pattern, and we have library, so we can identify. Okay, this we can find some cleaner. Okay, based on your fingerprint record, you are a cleaner, right? Like that. So if you find a specific pattern, and then okay, this is a taurine dioxide. Okay, we can define, confirm the chemical. Okay, and this is a signal to noise ratio, Sn ratio. So Sn ratio means signal. This is signal. Noise is this one. So if the concentration is high, and or sometimes the instrument is very nice, and then we can get high Sn ratio. Okay. But instrument is not so good, and the concentration of Thai chemical is very low, and then we get noise level is high relatively, so we can get low Sn ratios. This is a very basic concept for identification and quantification guideline for chemical. So generally, Sn ratio 2.5 or Sn ratio 3, 2.5 or 3 is guideline for we can identify. Below this the level, this noise level and peak level cannot be perfectly distinguished. And for the cases, we say it's not detected. Okay, the EI is generally good options, but for the case of very soft chemical, they lose molecular weight information. For the cases, we can use CI, chemical ionization. This is very soft method. They do not use electron. They use some gases, nitrogen or argon or some ammonia. Okay, so using this gas molecule, they make a positive ion or sometimes negative ion. So PiCi or NiCi or NCi we say. Okay, like this. N plus the other chemical produce another positive ions. This is soft ionization method. But right now we mostly use EI. Still we use EI is general option. For CI, only different chemical you can use. Okay, CI source is the same as EI, but except filament, there is no electron beam, but only we can add reagent gas to ion source. Okay, the structure is very similar. And third option of ionization is ESI, electrospray ionization. So this is widely used for LC, combination of LC. Liquid sample enter into this ionization chamber, and there's a water drops. Okay? Water drops become smaller, and finally the ion can make. Okay, like this. Okay, this is water sample, and then it becomes smaller, evaporation, and finally it becomes positive ions. So this is a principle of ESI. Okay? So this method is widely used for bio study. Biomolecule, okay, protein, and sometimes DNA. So this is ESI, EI is mass spectrum, ESI, electron spray ionization mass spectrum. There are many charges. Okay, so biomolecule have a large molecular weight, and large molecule they have opportunity to get the protein tip, or they lose many electrons. In other cases, they show many different peaks. But it is single peak for this one, and for this one, single peak. Different chemical, they can show different peak because of MOG value can be changed. plus 2, plus 3, plus 4, and so on. Okay? So based on some mathematical formula, we can calculate this into a single peak and this into single peak. This is called the convolution method. But it's a good concept when we can see it. Anyway, EI spectrum generally show many peaks, but it is a fragmentation. But ESI, the peak is not for many fragmentation, but by many multiple charged ions. There are many multiple charged. Okay. So they have shown many peaks, but only several peaks can be selected like this one. So mass spectrum. So again, the mass number with elements with charged Z values, N plus ions, and also fragment ions. There are many fragmentation limitations, and we call base peak. The most intense peak of mass spectrum is called base peak. So base peak is our molecule, and then it's 5. So this is an example of EI mass spectrum of methane, and 16. And then rules of 1 electron, 1 hydrogen, 2 hydrogen, 3, and so on. Okay, this is a typical mass spectrum of methane. But for these cases, mass spectrum is much more complicated. When we just use single chemical, but they have many isotopes, for example. Okay? For example, carbon 12 and carbon 13, and bromine and chlorine, they have also many isotopes. Okay? For the cases, for N plus ion, MOC values, 1, 2, 3, 4, measure 4 peaks. But this is only one chemical, one ion, M plus ion. This is due to isotope. This is rather very complicated concept. Okay? We analyze single chemical, very few chemical. But the chemical have isotope. So they show different peak with a slightly different number. So for many cases, we just take a nominal mass, so the average value. Okay? H2O, just 18. Okay? Nitrogen, 14. Hydrogen, 1. Carbon, 12. But in the reality, okay, there are many isotopes, so we can analyze that this way. Okay? So CHBr2, rules of 1 growing here, and another fragmentation. So this is a typical mass spectrum induced by isotopic elements. So but we have no problem. So this is where listed as a library, and software can automatically evaluate what is this chemical. And isotopic patterns, chlorine and bromine, xenon. So for POPs, chlorine and bromine is important. The abundance of bromine isotope is very similar. The ratio is 1 to 1, very similar. But chlorine is 35 chlorine, 37, is the ratio is about 3 to 1. Okay? So any chlorine, if we analyze pure chlorine, just chlorine, then you can get 2 peaks. So if there are 2 chlorine, Cl2, 3 peaks. Okay, 4 chlorine, 4 peaks, 5 peaks, and so on. It's a combination of some possibilities. It's very complicated, but we don't worry about it. Okay? So, for example, this molecule, so there's 9 carbon, 3 nitrogen, and 3 chlorine. So we can consider carbon isotope 12 and 13, and chlorine isotope 35 and 37. So 1, 2, 3 is basic peak by chlorine, a small peak here, here is induced by carbon 13. Okay. You see here, so carbon, all the carbon is 12, 9, and 12, 8, and the third carbon, single carbon. Okay. One difference. Okay. So this is the reason why we show generally observe so many different peaks, small peaks. But this is due to all the atoms isotope. And resolution is one of the important issues. So R, we say R. R is calculated like this: M, molecular weight, and delta M, between nearby. Okay. So for these cases, delta M is here, delta M, and M is the molecular weight of this peak. So R is high, large, very large number. It means that the peak can be perfectly separated. But R is low, it means that peak can be overlapped. So high resolution MS means they have a very high number of R. Even very similar molecular weight compounds, they can be separated by high resolutions. So also we can say it is visually power. Visually power. Okay, this is an example of resolution. At the same resolution, R is 500. The small molecule, molecular weight is 50 and 51. Okay, and difference is 1 unit. And then the molecular weight, R resolution is 50, 500. For these cases, molecular weight is 500, large molecule. And this can be also resolution R is the same as 500, but peak is a little bit overlap. And higher molecule is much more overlap. So when you say the same resolution, but based on their molecular weight, is separated where and separated it's not separate. So fortunately, our target chemical is less than 400. 4 or 300. So usually use high resolution numbers of 10,000, more than higher than 10,000 is enough for the separating dioxin and other chemicals. So other issues for resolution, for example, R thousands and 10,000 and 20,000. Okay, so when we use low resolution MS, you can just find one peak, and then you can think, okay, there is one chemical. But if we use high resolution MS, we can say, okay, there is two chemicals. Okay? So this is why we use HRS. And also, this is a very complicated example, but the concept is simple. Here is a molecule C16H12O and Si. Carbon and hydrogen, oxygen, and silica, they have all different isotopic patterns. So this is all the possible combination of molecular weights. Okay? The amorphous value, exact amorphous value is quite different, but the same compounds. But when you use HRMS, you can distinguish all these kind of chemicals. Again, for the isotopic pattern of large molecule, it's a small molecule. The amorphous value is about 1,000. Okay. For large molecule, we show more peak. It's more complicated to duplicate the mass spectrum for large molecule. Okay. So this is an EI mass spectrum. So EI electron impact is not good for large molecule. For their cases, we can use ESI, electron supporting ionization. And this is another example. R, according to the increasing R, we can measure the different patterns. Okay, common method analyzers. So far, I explained ion source, electron impact, chemical ionization, and ESA. And then, after ionization, how to separate this ion is a method can be done by method analyzers. Okay? There is actually so many different types. Top, time of flight, top, magnetic, etc., and colorful ion trap. This is just PCA ion trap. This is a colorful ion trap type. This is ICR, ion cyclotron resonance. So their option is to use colorful. Okay, the top is based on, actually there are many equations, but this is important. Energy is this one, the moving energy, kinetic energy equation. This is very basic physical equations. Okay. M, molecular weight or mass. V is speed. So when we input the same energy into different molecules, okay, the molecule get the same energy. Then the M, small molecule go fast, but the large molecule goes slow. Okay. It's like the same as people. Big guy and small guy, I push the same power. The big guy just stay there. Small guy go to that location, right? The basic assumption is that you put the same power. Okay? And then moving speed can be changed. This is a principle of time of flight. The flight means in a vacuum system, the ion flies, move. Okay? So this is a type of linear flow. You push the ion and then it goes to this way. Smaller molecule go faster. Okay, large molecule go slowly. And this is a reflector top type. There is a reflection. It means that it gives more patterns. More patterns means more separation of chemicals. Okay, long distance can be provided. So, TOP is a very powerful tool to separate the ion with their mass, okay, based on the time difference. The second one is magnetic sector or electric sector. Their principle is very similar. The magnetic sector. Here is a magnet, and then there's some. If there's a neutral molecule, and neutral molecule is not influenced by magnetic or electric field. Only ions can be influenced by magnetic or electric field. Okay, so this is about that equations. Okay, like this. This is a magnet for the MS. So you can see here, okay, B and I F values in the right hand side. Probably in the middle school days. Probably you didn't remember. But sometimes left hand rule or right hand rule. Okay? So this is right hand rule. Okay? Thumb, iron thumbs. Okay? B index finger. Okay? F the force and some magnetic field. Okay? So this is about concept. When there is a magnetic field or electric field like this way, an ion try to go this way, but because of electric field or magnetic field, ion can move like this way, okay, by this field. So based on this concept, large molecule, they tend to go straight. For small molecule, they be more neutral. So like this. So based on their mass, okay. So large molecule is go this way and smaller molecules go this way. Okay. based on their molecular weight. And this is a combination of double focusing means the combination of electric field and magnetic field. So we can get more visual power, the high resolution when we use both instruments, magnetic sector and electric sector. So for the conventional actual MS, we generally electric sector, magnetic sector, and then again electric sector we use. Actual mass will the spec they provide this type. So it's very strongly separate I. So we say, so this instrument result in high resolution. So we can say high resolution. Yes. So this way. Okay. So this is Japanese HMS, electric field, and magnetic field, and electric field. And another option is quadruple core. This is very basic measurement measures for small scale MS. The quadruple quad is 4. There are 4 rods. 4 means some rod. Okay. There are 1, 2, 3, 4. So okay. So this rod has connected with DC and AC voltage. The electric changes the plus minus positive, plus minus in 3 dimensions. Okay. So the ion, our target ion is positive, right? N plus. And then the ion tries to pass through this space. And then if the ion this rod become the positive plus and minus, and then our molecule tends to go this way. Okay. Again, so there are 4 rods this way, and then ion try to go straight. But ion is positive, right? So right side rod becomes positive and left side is negative, and then I tend to move this way. And such time later, they shift the direction from positive to negative, and then the ion becomes this way, and so on like this way, plus minus, plus minus. Okay? And then another, okay? This is a 3D structure. So the ion path will be like this way. Okay? And using this some electric conditions, only our target ion can pass through and enter into the detector, but other ion can be ejected to outside of this particle. So this is a quadruple principle equation, also DC and RF. You don't need to understand this equation. Just think there is some change of electric signal and the ions can be in the 3D structures they can move. Okay, so this is okay. So ion trap is principle is very similar to as protocol, but ion trap is 3D structure, more small ion sources. Small type of ion source, and so ions molecules enter into this space, and then there's an electron EI, and then so the molecules, some ions ejected into the outside, but our target ions remain in this trap, and then they enter into the detector. Okay. This is a kind of small scale 3D structures quadruple. Okay. Principle is very similar. One of the good points for ion trap is that within this ion trap you can do tandem MS. Okay. MS. It means that MS means, so single MS means there is a electron impaction, and then the ion, neutral molecule become ion. This is NS. And then additional electron impaction, and then fragmented ion become further fragmented. This is another NS. We say tandem NS, NS, NS. So in this ion trap, the NS can occur within this area. So with a further sophisticated instrument, you can do NS using ion trap NS. But the ion trap NS is used for some the high concentration chemicals, not for general pumps. This is a hybrid mass analyzer such as Q-top. Q means triple quadruple. Okay? Q. Quadruple. Q. And top is time of flight. It's a combination of quadruple and top. It can be more good result, more good separation of chemicals. So we say Q-top. Okay, this is a hybrid mass analyzers. So much more expensive than the original, the single top from MS, the total programs. So after passing through mass analyzers, our ion enter into the detector. Okay? So this is an electron multiplier. So a small amount of ion enter into detectors, and this ion signal should be converted into some electric signal. So it makes many electrons for the data recording. Okay? So consider that. So in this sample, we make a very small amount of final extract, and among them, only 1 microliter or 2 microliter enter into GC. There is separation, and also there is an electron infection, but only small fraction of neutral molecule become ionized. Okay? Then after mass filter such as colorful and magnet, only small fraction further arrive at detectors. It means that very small signal. So we have to multiply this signal using this instrument. So this is a discrete diamond electron multiplier. So there's a separated panel diamond, and first ion beam enter into this channel, and then there is a more reflections of electrons. So finally, it gives small signal become very large signal. Another type is channel electron multiplier. This is a discontinuous, okay, discrete. Okay, there is separation of elements, but this is a continuous regression. This is a linear type, and this is just a cubic type. Okay. This is a micro channel plate. This is much more small linear channel tube, and then the ion enter into this channel like this way, and there are very many diffractions. And then second step and third step, more stronger signal can be made. Okay, this is the overall instrumentation of sector type, MS, magnetic sector. Okay, here is a layer from the sampling system. So GC, from GC, our molecule, neutral molecule, enters into ion source. There is an ion source here. Ion source, there is an electron beam, continuous electron beam, and neutral molecule become ion. Okay, colored ion here. So this is a neutral molecule, and these colored dots are ions. So ion enter into this pathway, and then separates by magnetic fields based on their molecular weight. Light ion, and this is a heavy ion. light ion more influenced by electric or magnetic field, and heavy ions both have a tendency to go straight. Okay, so these changing differences can be recorded as their molecular weight difference. Okay, and finally, ion enter into the detector, and then there is a electron signal multiplications. Finally, computer calculate this signal into some mass spectrum or quantum mechanism. And this is colorful overview. Okay. Again, to get chromatography, we work right into and become ionized here to filament electron emissions, and then separation in this area within colorful, and only our target chemical we can enter into ion detectors. So, okay, this is review scheme of the mass spectrometer. For sample inlet, for POPs, we use GC or AC, and EI for ionization, neutral molecule should be the ion, so we generally use EI. Or sometimes the molecule is very soft to weak, and then we use CI, we add, use some gas. And the chemical is also very soft and large molecule, and then we use ESI, electro spray, for liquid sample. But ESI is liquid with AC, not GC. And the magnetic sector, electric sector, we use this one, double focusing, and for high resolution. And for the pHs or some other pesticide, we can use colorful type, and ion trap also. So also we can use top. Okay. So this is very basic concept. So whenever you get some information, advertisements, or brochure, or other books, probably you can understand basic principle specific. Okay, this is the last part, new analytical method. So in these figures, the new paradigm of hand means that so far we heavily depend on HRMS. But as I explained, HRMS needs high cost and very well-trained personnel. It takes longer time for analysis. And also sometimes pre-treatment procedures, extraction and cleanup, also cost. So we can use new method, or we can use simple treatment and low cost. Okay, so last month I attended Dioxin 2017 conference held in Vancouver, Canada. So the Dioxin conference is one of the famous conferences in this field. Okay. So in short, we say dioxin, but the frame of this conference is some halogenated organic compounds and so on. So any organic compounds, POPs, are the main chemical in this conference. So there are more than 30 sessions. Among them, there are 4 sessions for new instruments. Okay? So new method of analysis, and second one is new and alternate instrument method, and third one is non-target screening and determinations, and the last one is development of comprehensive technique for complex instrument. So this is called also environmental forensic. The forensic means so criminal investigation. We generally use this term forensic. Recently, we also say environmental forensic. So environmental forensic was well known for identification of oil spill. So based on oil spill chromatogram, we can decide this oil from which country, Texas, Alaska, Saudi Arabia, and so on. So we say oil fingerprint. Okay, this is the first application for inverted forensic. And also many methods can be also used for POPs forensic. So I mostly during this conference, I just in the conference sessions sometimes attend, try to listen to lectures. He's my boss in Canada, professors, the University of Toronto. He's famous for the multiple vector modeling and picture sampling of POPs. And also he is Dr. Tom Hammer at University of Canada. So he's also famous for picture sampling of POPs. So probably you can see some many information from the Stockholm Information website. They provide, they do some global monitoring of air. So for that purpose, they use patch-based sampler. So both this professor and this guy provide patch sampler to the many countries. Okay, from these sessions, the main topic is this one. Okay? From HRNS to different type of instruments. GC, tenor, MSNS, GCQ, quadruple, triple quadruple, say, triple quadruple, TQ, and top, the combination, the hybrid MS top. And GC high or GC times GC top. There are two GC columns. The chromatogram is one-dimensional chromatogram, but when you use this one, two-dimensional or three-dimensional chromatograms is possible. Okay, and so on. So this is a new instrument. And also another issue, the first issue is this one, using different instruments for POPs analysis. And the second one is from target analysis to non-target analysis. So previous analysis is a target analysis. It means that there are target compounds. Okay? We want to analyze dioxin, or we want to analyze PCB. Okay? This is a traditional method. But non-target analysis is that without specific purpose, we want to analyze everything here. Okay? For target analysis, we have to only select dioxin. So we need two very long cleanup procedures and high resolution MS to only select dioxin. Okay? This is a target approach. Non-target approach is that not only dioxin, but also many other POPs and or other POPs like chemical, we want to analyze everything and to see which chemical is newly detected. Currently, we only focus on Stockholm Convention POPs, but it's not perfect. There are many other type of POPs like compounds, so we want to analyze. This is non-target screening. The scanning and non-scanning instrument. Scanning instruments, this one,